So we are getting into the next chapter, talking about work and power, and we talked about energy before. Now we're going to apply those to actually doing something with the energy, and we're talking about work and power. So we're going to be jumping into that. Just in case you were wondering, that isn't me. I know it looks like me.
No.
Yeah.
No. It does look like me.
Yeah. There you go. So energy, we talk about energy as the ability to apply a force over a distance. And the same concept, force and distance, have to do with work. So if we're talking about how much energy does something have, that directly relates to the work that it can do. And we use joules to measure both of them. So you have a certain number of joules of kinetic energy, and that can turn into a certain number of joules of work. And so work and energy are very, very similarly related ideas. We tend not to think about thermal work and potential work. There's only certain kinds of energy that do work. Work, we're looking for something to have been accomplished. But it's the same formula. A force applied over a distance gives you work, and we measure it also in joules. Okay? So me standing up here is, if I'm standing still, I'm not doing any work. But if I start to walk around, now I'm doing some work. I am resisting gravity, and I am moving my keister around the room, and I'm expending energy to do this, and I'm doing a certain amount of energy, or I'm applying a force over a distance. I'm doing work, right? If I want to talk about power, power is not just force and distance. Power is force, distance, and time. When we talk about having power, we talk about the ability to do work in a certain amount of time. Okay, so think of a very slow-moving creature like a sloth or a snail. You know, a sloth will take all day to climb out of a tree and go to the bathroom and climb back up the tree. Like, that could be an all-day project for a sloth. But something like a squirrel could climb down from that tree, use the restroom, and climb back up the tree. And the squirrel could be done in, a minute, but a sloth took all day. The idea there is the same amount of work, applying a force over a distance, but in a different amount of time gives you a different answer for how much power was expended. The more power you have, the quicker you can do your work. So work in joules is force times distance. Power is work divided by time. The more power you have, the less time it takes to do the work. Okay? So power is a measurement of how fast work is done, and we measure it in watts in honor of James Watt, who was a mechanical physicist, among other things, but he did a lot of work in this area. He actually worked a lot with steam engines as well, and so we named the unit of power after him in honor of him. So here's an example. If Mr. Alley bikes up Kaanumanu from Pearl Harbor to the school, he did work to gain 72 meters of elevation. So that's just looking at the vertical axis of the work that I did, and it's ignoring the fact that I biked 1.4 miles. But to go up 72 meters, that's what we're going to look at. Okay? So the work that I did, I used to weigh 110 kilograms. I don't anymore. But let's say I did still weigh 110 kilograms. I had to move my 110 kilograms up the 72 meters, and I just realized that's not correct. Hold on, pause. Okay, so I fixed my mistake. My 110 kilograms is my mass, but I'm resisting gravity at 9.81 meters per second squared. So force times acceleration, that will give me my, mass times acceleration will give me my force, and then force times distance, giving me 78,000 joules. There you go. So it doesn't matter if I walked, jogged, biked, or ran, or climbed a ladder straight up. I did the same amount of work, because mass and acceleration is force force times distance is work, 78,000 joules. So we're just looking at the vertical aspect of climbing up the hill. I could have set a ladder at my front door and gone 72 meters up, and I would have done the same amount of work, okay? So it doesn't matter how you get there, it's the same amount of work, but it will be different amounts of power. Okay, so the difference between walking here, or riding my bike here, or running here, or driving a car here, is not in the work that I've done, but in the power that I've expended, okay? So biking takes 14 minutes to bike up the hill, and when I do that, I do 78,000 joules of work in 14 minutes, and I've got to convert that to seconds because we always use seconds for time. So 78,000 joules divided by 840 seconds, I spend 93 watts of power to get here on my bike, okay? When we walk, it takes about 25 minutes, and so same amount of same amount of work, 78,000 joules of work, but now I'm going to do it in 1,500 seconds because we're walking, and that takes less power, 52 watts, because I'm spending less power, so the same amount of work takes longer, okay? So when you hear a unit of power called watts, the more watts you're spending, the more work you can get done per unit of time. So doing the same amount of work in a longer amount of time takes less power. Does that make sense? Alrighty. There we go. Okay, so how much power does it take to push a rock across a field with a force of 19 newtons for 20 meters in 1 minute? So my force is 19 newtons, and I'm going to do that for a distance of 20 meters, and I'm going to get that amount of work done in 1 minute, okay? First we need to find the work done. So work is force times distance, 19 newtons times 20 meters. 19 times 20 is 380 joules of work. Then we can take into account the time elapsed. So power is work divided by time. So 380 joules of work gotten done in 1 minute. We've got to convert that to seconds, 60 seconds. So 380 divided by 60 is 6 1/3 watts. I would need to correct for significant digits. I had 2 significant digits here. I had 1 significant digit, 1 significant digit. So I said 6.3, but I should have actually rounded to 6. It takes 6 watts to move the rock in 1 minute. Okay? So that's how you use power and energy. You guys understand the idea? Beautiful. So the other way to get work done quickly or easily is to spread out the distance over which you do the work. So work is amount of force times the distance that you do that force for. Well, if I want to get the same amount of work done, and I want to apply less force to get that work done, I have to do that less force over a greater distance. So you can see this just algebraically. If I have 100 joules of work to do, and the normal way to do that is to apply 50 newtons of force for 2 meters, I could get the same amount of work done, the same 100 joules of work. I could do that same amount of work if I did 10 newtons of force for 10 meters, right? So you can see that algebraically. You can have the same product. If you make one factor smaller and the other factor bigger, you can still have their product be the same answer, okay? And so a simple machine is a device, a tool, that gets the same amount of work done by lowering the force that it takes and increasing the amount of distance over which you do that force. Okay, so that's a simple machine. There are 6 classic simple machines, and we're going to go through them very quickly. Okay, So take the same amount of work and spread it out. If you have a lever, that's one of the simple machines. This guy's got to lift a rock. Well, he could just walk over behind the rock, squat down, bear hug it, and stand up. And he'd be sweating and grunting, but he'd be able to lift the rock. Or he can take a pry bar, and he can find something to use as a fulcrum, a smaller rock. And then by using a pry bar, he can lift the rock. And what he's doing is he's only going to lift the rock this far. But he's going to push the lever down this far. So see, he's pushing the lever down further than the rock is going to rise. So he is taking more distance to do this amount of work. And so because he's taking more distance, the force that he has to apply is proportionally small. Okay? So a lever is one example of a simple machine. A pulley is another example of a simple machine. If you have to lift 100 pounds, then you could either grab it and lift 100 pounds. Or you could use a two-pulley system, and you are going to be able to pull with only 50 pounds of force and raise this 100-pound block. So it's cutting the amount of force required in half, but you're going to have to pull twice as much rope through this system as the distance that this raises. So if you're going to raise this 1 meter, you're going to have to pull 2 meters of rope through the system to get this to go up 1 meter. But you only spend half the energy, half the force over twice the distance to get the same amount of work done. Okay, so it's easier, but it takes longer. A screw is another one. So, not that anybody has a really hard time lifting up a Cheerio, but if these are heavier things than Cheerios, you can have a screw, and the Cheerios, the force of gravity pulling the Cheerio down that you've got to overcome, the weight of the Cheerio, is going to be done over a very, very long distance as it goes up the screw and falls into the bowl of milk. But the much greater distance that it's going to travel means that it's a lot less work. Okay, sorry, same amount of work. I keep using that word wrong. Same amount of work, less force over a greater distance. So we're increasing the distance, decreasing the force, and getting the same amount of work done. And here's an inclined plane. This guy's got to load boxes of copy paper. He could pick up the boxes of copy paper and put them in the back of the truck and directly do that amount of work. Or he can use an inclined plane. And now he's gone from having to lift the box this far to having to carry the box this far, right? Much greater distance. But by increasing the distance, he decreases the force that he has to apply. And so it's easier to get that same amount of work done. You just have to do it over a greater distance. Okay? Here's a hammer and a wedge. A wedge, you've got to split this board by this far. And you could either grab a ridge of the block and go and Hulk open that block, right? Good luck with that. Or you use a splitting wedge and you take all of this amount of distance along one of these edges of the wedge, and you take that same amount of work of spreading this block and multiply it over this great big distance, which means it takes a lot less force. Same amount of work, less force, greater distance. Okay? So those are simple machines. Mechanical advantage is how we analyze a simple machine. Mechanical advantage is calculated as the ratio between the force you put in and the resulting force that the machine produces. Okay? So mechanical advantage is a division question. How much force do I get out of this machine divided by how much force I put in to the machine? So it multiplies my force, but we're going to see in a moment it has a price to pay. It multiplies your force by increasing your distance, right? But mechanical advantage says how much force did I get out of this thing divided by how much force I put into it. And I'll pause and let you get caught up in writing that. Okay, so let's apply this. We've got a very, very, very heavy cannon. Okay, 300 kilogram cannon. And a warship, the HMS Belfast, which is a warship you can go tour if you are in London. Did you guys, oh no, you weren't there, who was there? Did you go tour the Belfast? You did? See, it's a good time. HMS Belfast loads a 300 kilogram cannon onto its decks by using a pulley system. A deckhand capable of pulling with a force of 100 newtons is able to lift the cannon using this system. So what is the mechanical advantage? Here we go. First, we need to know how much force the pulleys put out, right? So force is mass times acceleration. So it's a 300 kilogram cannon, and it's being pulled on by the force of gravity, 9.8 meters per second squared. So 300 kilograms times 9.8 meters per second squared gives us a force of 29,040 newtons. Okay, and that's not correct for significant digits, but I'll round at the end. So the pulley is the mechanical advantage is the resultant force divided by the effort force. So the resultant force is 29,040 newtons, 2,940 newtons. There you go. And the effort force, the little scrawny deckhand, can only pull with a force of 100 newtons. And he's able to do the work. So he pulls at 100 newtons. So 2,940, 2,940 divided by 100 is 29.4. And notice this is newtons divided by newtons. So my unit of measure, there is no unit because all the units cancel out. Newtons divided by newtons. This is just a ratio. 29.4 is the ratio. Okay, there's no unit there. So the block and tackle system magnified this puny deckhand's force by almost 30 times. And so it's a whole bunch of ropes that would go through that block and tackle system so he can raise the cannon. Now we know that the reason he's able to do that is it magnifies his force, but it increases his distance, right? So while it multiplies his force by about 30 times, he'd have to pull about 30 times the rope through that system to get that cannon to raise. All right? So we're going to look at that now. The same question of mechanical advantage, looking at the price to pay. Another way of looking at the same situation is by analyzing the distance of effort divided by the distance of resistance. And it gives you the exact same answer, but it's flipped. The first time we did, what do I get out divided by what I put in? And now we're going to do, how far do I have to move divided by how far does my load move? So you're going to get the exact same answer because for mechanical advantage, it's magnifying my effort by increasing my distance. So the ratio of my distance of effort divided by my distance of load or my distance of resistance is going to be the exact same answer as my distance, as my force out divided by force in. Okay, the only thing you have to keep in mind is that you flip. On the other one, it's what I got out divided by what I put in, and this one it's how far I go divided by how far my load goes. Okay, but mechanical advantage is going to give you the same. So whichever one is more convenient to use, the change in distance ratio or the change in effort ratio, you can use either of them and get the same answer. Okay, so another way of looking at this is to say, how much rope did the scrawny sailor pull through the block and tackle system to raise the cannon, the 4 meters from the dock to the ship? So he's got to get this big cannon 4 meters off the ground and then swing it into the ship. We already know the mechanical advantage was 29.4. Okay, so the ratio of effort to resistance is going to also be 29.4. So we can use that mechanical advantage ratio. 29.4 equals the distance effort divided by the distance resistance. So the distance resistance here, how far did he have to move the load, was 4 meters. So we can plug that in. 4 meters. And then to get distance effort by itself, I need to multiply both sides by 4, right? Multiply this by 4, multiply that by 4, and I get distance effort by itself. Distance effort then is 117.6 meters of rope. He had to pull a lot of rope through that block and tackle system. But he was able to raise that huge cannon with much less effort. So in order to make the work almost 30 times easier, he had to move almost 30 times the rope. Okay? And that's the way that it works with all simple machines, is you don't get something for nothing, right? It takes the work. You can either do a whole lot of people pulling on the rope for a short distance, or one scrawny dude pulling on the rope for a lot further, and get the same result. Okay? Any questions? Yeah. All right.